Russia's plane with backward wings, the Sukhoi Su-47. This experimental fighter served as an example of how contemporary materials make it possible to do previously unthinkable things. There was only one airplane manufactured, and it was never assembled, but it offers a wealth of important information for Russian aviation experts. According to a TASS report that describes the development of the Su-47 fighter, the enormous knowledge of the reverse sweep wing constructed of composite materials gathered during the Berkut tests is used in the creation of unmanned aerial vehicles. By reducing inductive drag, the swept-back wings enhance subsonic flight range, agility, and takeoff and landing characteristics. The paper does not specify how much of that experience was applied to the creation of Russian drones, though. It is thought that a plethora of knowledge was produced during the Su-47's construction process that was very beneficial to the Russian aviation industry in developing current aircraft. Western defense specialists and the media paid close attention to Berkut as it was being developed. The fighter of the 21st century, it was right away nicknamed, and news of its mass manufacturing plans received a lot of media attention. To update the Su-27 fighter jet for the USSR Air Force, a project to build an aircraft with a reverse sweep wing was launched in 1983. The USSR Navy was looking for a new fighter to fly from an aircraft carrier at the same time. The fighter was renamed the Su-27KM, but after the fall of the Soviet Union, development was put on hold. Throughout its development, the fighter plane went by several names, including S-22, Su-27KM, S-37, and ultimately Su-47. The Su-47 was first made available in January 2000, and the first round of flight tests was finished in December 2001. Sukhoi was chosen as the primary contractor for the Russian PAK-FA fighter program's fifth-generation model in May 2002. The PAK-FA fighter jet is a derivative of the Su-47, but does not have wings that sweep forward. The PAK-FA fighter plane's initial flight test was accomplished on January 29, 2010. The avionics and aerodynamics technology created for the Su-27 upgrade program served as the foundation for the design of the Very High Maneuverability prototype. The Su-47 maintains maneuverability in supersonic flight and has unusually high subsonic agility, allowing the aircraft to quickly change its angle of attack and flight path. High levels of maneuverability, stability, and controllability are maintained at all angles of attack by the Su-47 aircraft. When the mission may require fighting successive targets in several airspace sectors, maximum turn rates and the upper and lower restrictions on airspeed for weapon launch are crucial factors in determining battle dominance in close combat as well as at medium and long ranges. The Su-47's fast turn rate allows the pilot to quickly point the fighter jet at the next target to start the missile launch. The oval-shaped Su-47 fuselage is made primarily of titanium and aluminum alloys, with 13% of its weight made up of composite materials. To enhance the aircraft's anti-spin capabilities, the nose radome has a horizontal edge and is slightly flattened at the fore section. The two-perm Avid Vigitel D30F6 turboshaft engines power the Su-47 fighter jet. Each engine has a dry thrust capacity of about 43.4 kN. The engine is used to convey passengers in short-range aircraft. The engine has a length of 3.98 meters, a fan tip diameter of 1.05 meters, a dry weight of 1,550 kilograms, and a delivery weight of 1,712 kilograms. The engine also has a low-pressure compressor and thrust reverser. The Su-47 is comparable in size to earlier, bigger Sukhoi aircraft like the Su-35. The Su-47 used the forward fuselage, vertical tails, and landing gear from the Su-27 family to cut development costs. Nevertheless, the aircraft has a weapons bay inside and a compartment for sophisticated radar. The Su-47 has a tandem triple layout similar to its recent predecessor, the Su-37, with canards placed in front of the wings and tailplanes. Two tail booms of different lengths are located outside of the exhaust nozzles on the Su-47. A rear-facing radar is housed in the taller boom on the left, while an ECM system is housed in the shorter boom. The Su-47 has an unusual appearance due to its midwing that is swept back. The inner half of the wingspan accounts for a significant component of the lift produced by the swept-back wing. Because wingtip stall does not limit this inboard lift, the wingtip vortex formation caused by lift is decreased. The airplane can still be controlled even if airflow separates from the rest of the wing surface because of the ailerons. The control surfaces of the wing are still effective at the highest angles of attack. In contrast to a similar straight or aft-swept wing, a swept-backed wing exhibits geometric wing twisting when it bends under load, which puts more stress on the wing. This necessitates the wing's design to twist in the opposite direction of the geometric twisting when it bends. This is accomplished by twisting composite wing skins. The aircraft's maximum speed at first was Mach 1.6. The swept-back wings provide several benefits, but creating one is difficult since at certain flight speeds, the entire structure can shatter. High stiffness properties were made possible by the use of composite materials. Nowadays, composite materials are frequently used in the production of aircraft. By 1990 standards, Bearcoot's creation of the framework for the development of these technologies was a major milestone. Rostech's Obninx research and production company, Technologia, which makes the panels for Bearcoot's reverse sweep wing, was given the assignment. The panels were made of a brand new material developed by VM that performed better than the best materials available in the 1980s. However, the aircraft was able to use several groundbreaking designs and technical advancements that had never been used on an aircraft of this class. This calls for the use of longitudinal static instability, the creation of huge double-curved milling panels, the use of composite materials in loaded airframe structure elements, etc.